Greetings, ladies and gentlemen. It is now the afternoon. Holy shit. All right. So it's been a little bit since we did. I say a little bit. It's been like 2 days since I streamed, and also coincidentally 2 days since I did C++. But I did look over my code to make sure I still understood what the fuck was going on, and I still do. The hardest part is remembering how to create different shits. So what we're going to do is we're going to go back into the video, the C++. Let me pull it up. We're on chapter 3 out of, I think it's 19 chapters. How many chapters is it? Yeah, 19 chapters. We're on chapter 3, variables and data types. I don't actually have any idea how long this is going to
In this
be.
chapter,
Hold on. I don't know how long each stream is going to be. I don't know. I don't have a plan for that because some of these chapters. Well, you know what? Let's just go over here. Code scene. Make sure my shit's pulling up. Do like this. Oh, it's capturing the wrong one. That's kind of annoying. Please capture the right one. See, now it's doing that one. There we go. See, I don't know why the fuck I wanted to do that, but it was wrong. Ugh. So, there's that. The other half of this screen is going to be my fucking code when I get to it. But if we look real quick at this one, like this is chapter 3, and then some of these just like, especially the later chapters, which I guess it kind of makes sense that the later chapters would be much longer, you know. But who knows? It took me fucking forever to just get through this, but hey, whatever. All right, let me. I'm just gonna have the video play, and then I'll open something when he opens something. So that will make our lives a little bit easier. Whoop! Hello, Tara. How you doing? Oh my gosh! Variables and data types. Now, if I had to guess, variables is just like creating x and y values, which seems like something that we would have already done, right? I don't know. I think it's probably best if I just play it instead of trying to speculate on what it could possibly be.
we're going to learn about
I'm a
variables
Waco.
and
Nice.
data types. Before we talk about variables and data
Oh
types, I
God.
would like to take a moment and recap on what we know by now.
Okay.
And if you look at these cards, many of these things should make sense now. You know about the main function, you know that it is the entry point of your program. You know that your program is going to be made up of statements, and
Yep.
statements end with a semicolon in C++. You know about functions, errors, warnings. You now have an idea about how you can handle input and output from your program.
Yep.
You
Yep.
can use comments. You know about the memory model and the execution model that we talked about in the last lecture. You know quite a lot. Now, we have been using a program like this to do things in the last chapter, but there is one thing that isn't really explained yet, and that is this int. This int is a type that is predefined in C++.
Right. It's an
And C++
integer, right?
predefines many types. Here we have a couple of
Veggie
these
bowls and dum
types
dum
for you to
types.
see as examples. Int is one of them. We have seen it a lot of times in the last chapter. It is used to represent
Oh boy,
whole
what is
numbers
float?
like 1, 2, and 3, but we have others. For example, double and float are used to represent fractional numbers.
Okay, so we have integers. These are whole numbers, obviously. Double and float, he just said, are both fractional numbers. I'm curious what the difference is. I'm sure we'll get to it eventually. Char, I have no idea. Boolean is like on-off type shit. I can't watch, I'm outside. That's fine, lazy. I appreciate you coming to say hello anyways. I remember using void in a fucking in Java once upon a time, but I'm sure it's a completely different meaning here. Tara has a pic. You have a picture of him being outside? He's repeatedly saying slurs, lazy. No, don't tell him that. I'm not doing that.
Numbers that have decimal points. For example, 2.5, 7.3, and numbers like that. And we're going to see the difference between these two. Another one that is commonly used is char or car, and it is used to represent characters in memory. And you can store
Characters in
in
memory.
characters like A, B, C, and D,
Oh,
and
okay.
all the other characters you can really put in. We have a bool, which is a type that is going to store two possible states. The only values you can really store in here are true or false, and we're going to see how
True.
this works.
Okay, yeah. So
Void
bool is true,
is
false, like I thought.
somewhat confusing
I think I said
because
on
it
off, but it's like the
represents
same idea.
a typeless type, and it
A
is really
typeless
meaningful
type.
when we get to talk about functions in detail. So we're going to learn more about the void type a little later in the course. We also have the auto type, which is really not a type. It is a keyword you use in C++ to deduce other types, and we're going to see how this works later in the course. These are a few examples of types we can use in C++, and we are going to play with most of them in this chapter.
Okay,
Another thing
good.
I really want you to see
I like learning
is
about
what
this.
does it mean to really put
I believe it.
a
No, you
for in a
don't
variable
believe
in
it,
a
lazy.
program.
What the
Everything we
fuck?
have in this program here is represented by ones and zeros in the computer's memory. It really looks like this. It's a bunch of ones and zeros in the RAM of your computer, and
I've
there
seen
must
this.
be a technique to
Not
make
this
sense
exact
of this
version, but
gibberish here and store data that makes sense to humans. And the starting point is to group these ones and zeros into little chunks that we can manipulate. Each of these ones and zeros is called a bit. So this zero here is a bit, this one here is a bit. And if we group 8 bits together, they are going to form what we call a byte. Okay, if it makes
a typeless type is that one hipster code that says they reject labels but has a new gender each week. Oh god. I've heard of I have a friend who knows people like this. knows people who are like close to them, like family. And it's one of those things that's very it feels very like, oh, I reject all labels, but then like their entire identity is in labels, and it's really funny because it's almost like a hypocrisy that they just don't understand. Void is mostly used for functions that don't return a value. So that makes it sound to me like void is going to be very, very important and will do a lot of things. Because I feel like returning a value is sure that's important, but I feel like it'll be I feel like it'll get very, very complicated with void later. Unless I'm like high as fuck.
sense, you can group your bits in bytes, or if it makes sense to group them in groups of 16, you can do that like we see here. We're going to see a little more details about
Don't we
this
use
in the next lecture. Okay, here you see that if you really
So he talked about grouping stuff into grouping bytes into groups of 16. Isn't that like the main reason to use hexadecimal? Like no like to read binary? Like you look at the hexadecimal codes and it's like, okay, does this shit make sense or whatever? I remember, so my short tenure at college, I remember one of my teachers talking about doing shit like that. I was also fucking I think also maybe some of my friends might have mentioned doing this before. Basically, like they had to look at like this long ass list of fucking uh like 3A fucking all this bullshit that they just couldn't fucking that required them to go through and find out why certain bits were doing the things that they weren't supposed to do.
You can treat each bit as a self-contained piece of data, but this is really not very useful, but there are some corner use cases for this. Okay, now we really have two sides. On the right, we have data in the format that is really convenient and understandable by humans. And on the left, we have how data is represented in memory. So there must be a way to transform between these two forms of data, because humans can't really handle these ones and zeros well. And we do the
Right.
transformation between these two representations of data using number systems. We have a few number systems available to us that we
binary
can
we
use.
use.
Binary, octal, hexadecimal
I know
are
about
a few
hexadecimal.
examples,
Octal I
and we're
haven't
going
used.
to learn about them starting in the next lecture. So go ahead and finish up here and meet me there. In this lecture, we're going to learn a little more about number systems. Number systems allow us to transform data from the form that is really convenient for humans in a form that is convenient for computers in these ones and zeros that you see on the left. We can also use them to do the reverse, go from ones and zeros and go in the format that is convenient to humans, like this 22 or this Steve name here. To make sense of how these number systems work, let's analyze the decimal system that we really use in daily life. And
oh god, okay, so this is 924. Wait, is this just... Is this... Wait, what the fuck? Why is it 10 to the 0? That's 1, isn't it? So 2 times 10 to the 3. So 2 times 1,000 plus 3 times 100 plus 7 times 10 plus 1. Oh, it literally is. It's all he's doing here is just breaking this. Why is it okay? Why? What
that
is?
is usually called base 10. So
yeah,
if
this
you look at
is this just demonstrating base 10?
Oh
no, numbers.
You can really split it in the form that you see to the right here. If you try and take this expression we have on the right here and evaluate it, you're going to get this number here.
Yeah.
2 times 10 to the power of 3. This evaluates to 2,000, and this
right.
one here
this
is
makes sense. I understand
basic
math.
This one is going to evaluate to 70, and the last
I just don't
one
understand
is
why
going to
we're
evaluate to 1.
breaking
and if
it down
you
like
add
this.
These things up, you're going to end up with this number. So this is how we can take a number and make up a base 10 representation of it. We can do the same thing for 924 here or 47 here. It really is basic math. You don't need to have a lot of background in math to make sense of this. So we're going to use this
I think the most confusing thing that he did here is he added the 10 to the 0 for some reason. Like, I get that that's just 1, but why?
Form and understand binary numbers. If you look at what we have here, we have a few binary numbers that are made up of ones and zeros.
So 1 times 2 to the 5th plus 0. Can't we just beam our ideas into the computer from our minds magically? If only, dude. If that was the case. All right, let's look at the simplest of this. 1 times 2 squared. So 1 times 4 gets you this. Is this just... oh, okay. So this expression is equals this? Is that all it is? Because it's just... This is like 7 in a binary. And then this one is like... it's like... Hold on. Oh, yeah, that's all he's doing. So this equals to 7, and this is just how it's expressed in binary. Is that all he's demonstrating?
That's why it's called binary, because you can only have 2 states, or 0 or 1 in your numbers. So we can really do the same thing. We are in base 2, so instead of using a 10 here, we're going to be using a 2, but it is the same operations we really did. If you take this and multiply and add these things up,
don't be squared number. This stuff isn't squarey, so be brave. Oh my god.
Of this number. If we go in the middle here, we have something we can easily do without using a calculator. The expression on the left here is going to evaluate to 0 because we are multiplying with 0. The second one is going to be a 2 because we are taking 1 and multiplying this by 2. The others are going to be zeros, but the last one is going to be 2 to the power of 4, which is 16, and we're going to add a 2, and this is going to evaluate to 18. We can actually bring up our calculator on Windows 10. I think it can help in this a little bit. We're going to bring it up, and we want to put it in a programmer mode, and we're going to go back on our slide and find our number
even
number,
know that
which is
existed.
10010. So we're going to type it out, 10010 in binary. This is binary that we have typed here. So let's clear this and do 10010, and you're going to see that in decimal it is 18, which is what
Your
we came
avatar
up
looks confused when its
by
head is tilted, and
computing
I think
this
that's
in our
apt.
brain. Let's try the one we had before that
I
we couldn't really do in our brain. We're going to say 100101. Let's do that. We're going to clear 100101. This is going to evaluate to 37 in decimal, and you can use calculators like this to really do the transformation.
So when we're looking at this, right, like he typed it into binary, so like this is the binary value, and it equals 37. But 37 written in hexadecimal is 25, and written in oct is 45. What the fuck? So I understand how binary works. This part isn't particularly new information for me. I'm curious what we're gonna have to do with binary, like specifically. Like, are there gonna be like exercises or something? I remember having to learn how to add stuff in binary, you know, because it's like really weird, and if you don't know how if you aren't familiar with the concept of using different number systems, whatever that number system might be, whether it's like binary, octal, hexadecimal. I mean, I learned how to add and shit in hexadecimal, but I was never very good at that. I get it, but I don't like numberinos. I don't like numberinos either.
Between these different number representations. Okay, down below we have a 111, which is going to evaluate to a 7 in base 10. Okay,
Right.
if we have 3 digits, we can really represent numbers between 0 and 7. And you see a table here that is going to prove that. 000 is going to evaluate to 0 in decimal. 001 is going to be a 1. And if you go down to 111, that is going to evaluate to a 7. You can try and use a calculator to prove this and really understand how this works. If we use the 3-digit representation, our numbers are going to look something like this in memory. We're going to take the bits in memory and group
3 digits in memory? It's 3 digits, but in binary still. Fun fact, this means that you can count up to 10,023 on 2 hands if you just do it in binary with each number representing a 1 or a 0. Onion squared. You know, Tara, you just reminded me of the fucking, there's a question in the Impossible Quiz that, it's an old Flash game, I don't know if you remember, called the Impossible Quiz, and it says the square root of onion, and the correct answer is shallots.
Them in groups of 3, and we are going to use binary to actually make sense of these numbers. For example, here on the left, this is going to be a 1. The second one from the left is going to be a 6, and this is going to be a 6 as well. This is going to be a 0. This is going to be a 3 because we have 1 and 2 here. We add those up, we get a 3. If this doesn't make sense, you can try and use a calculator. You're going to see that it makes sense. Okay, so
but
what if
why?
we want to group our digits in groups of 4? We can do that, and we're going to end up with something like this. The values we can...
Isn't 4 digits the more normal one? That makes no goddamn sense. Well, it's not supposed to. The Impossible Quiz is a bit of a... It's like half jokes. It includes things like Bridget makes everyone, and then the correct answer is gay because it's referring to Bridget Guilty Gear. But this is before Bridget was trans, according to that whole debacle.
Present are going to go from 0 all the way to 15, and you can try and
but isn't this how
the calculator like we just did, and it is going to look like this in memory.
4 digits isn't 4 digits what we usually use for reading in hexadecimal? You read like it's like 2 symbols or whatever,
formula that we can use,
or is it 8 symbols and like is it
memory? For
is
example,
it full bytes for one hexadecimal digit?
0, 1, 1, 0. If we go back to our table and find 0, 1, 1, 1 0. This is a 6. And we
Right.
need to know that these 4 bits here are really
I remember the
storing a
impossible
6.
quiz, but I never
And there are
finished it.
ways you can
I might try to
manipulate
finish
this
it on
in
stream one
your C++
day.
program. We're going to see that. You can also use
I remember
5 digits,
I
and
spent
you're going to
many
end up
attempts on it,
with
and it's just
something
hard.
like this. And the numbers are going to go from 0 all the way to 32. And this is how it's going to look in memory. You can try and come up with what this represents in decimal. I'm not going to tell you this, but we can try and figure out the one on the left here. So it is 0, 1.
So let's do these real quick. So we're gonna find these all in decimal. So this is what? So this represents 1, this represents 4, this represents 8. So this is fucking 4 plus 8 plus 1, fucking 13, I think is what this one is supposed to be.
101. If we go back, we're going to come up to 01101, which is a 13 here. So
all right, so that was easy. So 1, 2, 4, 8, 16. So this is 24. This is another 24. This is fucking. This is 15. This is 2.
this memory location, these 5 bits represent a 17 number. So if we
Intubbable
want to
game where
kind
you try to
of
teach Mildred math.
generalize
Oh
what
God.
we have talked about in the last slides, if you
It
have
reminds
one
me of
digit, you can really represent 2 states, 0 and 1. If you have 3
that makes me
digits,
think
you can
of Cherno's
represent
perfect
numbers
math
between
class.
0 and 7. And you can go all the way down. And if we generalize this in a mathematical formula, we can say that if we have n digits, we're going to be able to represent between 0 and 2 to the power of n minus 1. And if you try to plug in any number of digits, you're going to see that this formula works. Okay, so these are a few grouping of bits we have in practice. We can use 8 digits, and we can represent numbers between 0 and 255. If we
What is this fucking number? So we got hundreds, thousands, millions, billions, trillions, quadrillions, 18 quintillion, 446 quadrillion, 744 trillion, 73,709,551,615 fucking bits. That's a lot of fucking data. Holy shit.
have 16 bits, we can represent this range. If we have 32 bits, we can represent this range. If we have 64 bits, we can really represent a really huge range. I can't even say this number. It's really big. Okay, now you should have a pretty good idea of the binary system and different representations
we understand how that works.
use to make sense of binary numbers in
what I'm curious about
memory.
is why we're planning, why we need to know it, why we are going to understand what it's going to be used for later.
And it is a technique we use to shorten the length of how we represent.
Okay, so I was right. Hexadecimal is used for this.
How does it work? Well,
they didn't
we take our number
I was worried.
and split it in groups of 4 bits. And
okay,
each
so it's 4
group
bits.
is assigned a symbol we can
I
use
just say big number and stop reading after 2 digits.
Zeros, that's going to mean a 0 in hexadecimal. If we have 0001, we're going to represent a 1. And you can see that if we go up to 9, this is really similar to what we have in the decimal number system. But once we hit 10, we're going to represent that with an A in hexadecimal. 11 is going to be B, 12 is going to be C, 13 is going to be D, 14 is going to be E, and 15 is going to be F. So how do we use this to represent binary numbers? Let's see an example. Here we have a huge number that we represent in memory. It starts with 0 and ends with a 1 here. So the first thing we're going to do is to split this in groups of 4, and the one on the left is going to be a 1 1 1 1. If we come back to our table here, so 1 1 1 1 means F. So we're going to represent this with.
This is the hexadecimal value of this entire thing. That's fucking, I mean, that's way shorter. It makes way more sense to break it down like this than it does to try and read all of these 1s and 0s where you 6. So E would be what? That's is that 14, 13, 14? hold on. 1, so we have 2 plus 4 plus, so it's 14. And then this, okay.
Enough. If we
God.
go to the second group of 4
But
bits,
why do
we
we need to know
have
this?
0,
I'm
0,
not
1,
understanding.
1. If we go back, 0, 0, 1, 1 means 3. So we're going to have a 3 here. I hope this makes sense. And we're going to keep using the same transformations, and we're going to come up with 1F03E6. And we can represent this binary number using these symbols. You can see that we go from using 32 bits to using 1, 2, 3, 4, 5, 6, 7, 8 symbols to represent this. And this is shorter and easily manipulable by humans.
I woke up enough to notice you have a black screen behind you instead of the VS Code screen. Well, so I don't. I figured I would open it when he opens something, but I was not expecting it to just be just the lectures for all of this. This stuff I kind of understand, and I'm mostly curious as to its applications and why we're going to use it, because it hasn't really been explained in the video. Like, I understand that it is important, I don't understand why. And so I'm kind of, I'm sure that it'll come up eventually. It's kind of like with the when he was talking about like the way that it executes code and how it goes to different parts of memory, and I understand that it's important. I just don't understand why we need to understand that yet. I'm hoping that we find a practical application for it before we just before we completely fucking abandon this idea. And I hope that we use it relatively soon and not like, oh, we're learning this now, but we don't use it until chapter 10 or some shit like that. Because then by the time I get to chapter 10, I will probably need a refresher, which, I mean, I'm sure they would provide, but then why am I bothering with it now? That's...
And we use a 0x in front to mean that this is a hexadecimal number. I really hope this makes sense. So if we have numbers that don't really fit in groups of 4, we're going to go from the left and split this in groups of 4, and we're going to end up with a group on the left that doesn't really meet our requirements. And what we can do is add the missing bits and make them zeros, and we call this operation padding. This is what you can do to really represent any number in hexadecimal if you don't have enough bits on the left. We also have another system that is really not widely used.
So do we always group them from right to left then? And then we pad whatever's on the left? I mean, I kind of assume that's the case. But I mean, do we... Are we always going to be right on that?
Today, but I am mentioning it here for completeness. It is called octal system. It goes from 0 all the way to 7, and we can divide our binary number into groups of 3 and represent using these zeros and ones to shorten the length of the binary number. We can really do the same thing we did with hexadecimal. So we're going to take
0 in the front means that it's octal. 0x is hexadecimal.
The one on the left is going to evaluate to a 7 because it's 1, 1, 1, and 1, 1, 1 evaluates to 7 in octal system. The second one is also going to be a 1, 1, 1. The third one is going to be 1, 0, 0. If we go in our table, it's going to be 1, 0, 0. It's going to be a 4, and you see we have a 4 here, and you can do the same things until you have figured out the entire number here. And you see on the left we are doing padding and adding a missing bit and making it a 0. So we are coming up with 0, 0, 1. And if we go back to our table here, 0, 0, 1 is a 1. And that's what we put here. So we're going to put this number here. It's going to be 15, 61, 41, 70, 47, 7. And we're going to add a 0 in front to mean that this is a number represented in the octal system. I really hope this makes sense.
I mean,
so we
have seen
all these binary numbers and different number systems we can use to represent them, but how do we use them in a C++ program?
Yes, please explain.
Here is a simple example of how you can represent the number 15.
Okay. So 15 is decimal. 017 octal 0x0f hexadecimal, and then 0b000111111. Right, 00001111. Okay, so I'm going to assume. So, but without, we haven't gone forward. Is he getting to the code now? Maybe. We'll see. What I'm guessing with this is when we write just 15 like this, it understands it as just being decimal. But then if we put a 0 in front of it, then it tries to do it. Then it understands it as octal, and this is how we write it in octal into C++. And then 0x would give us the hexadecimal, and then 0b is in binary, which I'm curious. It's interesting that this is how that you're able to just write numbers into binary and into these different systems. I'm curious what the use of it would be, but let's see.
Through different number systems in C++. If you just say 15 like this, it's going to be in decimal. If you add a 0 in front, it's going to mean that the number is in octal system. So this can be confusing sometimes. If you do 017, it's not going to be 17. So if you say 017, C++ is going to interpret this number as if it is in octal system. And it is going to turn this into 15. Down here you see the same representation in hexadecimal. We saw that you use a 0x in front to represent that it is in hexadecimal, and this is going to be 15 in memory. And here we have representation in binary using zeros and ones, and you use 0b in front like this. I have to say that this was only possible since C++ 14. So if you are using an older standard of C++, you want to be able to represent binary like this. And if we run this program, it is going to print the same thing. It is going to print 15, but we stored the number using different number systems. Let's go to Visual Studio Code and try this out. Okay, here we are in...
Okay, hold on. We can do this. Actually, hold on. I gotta do this properly. Bah. All right, it should be opening. We're finally getting to it. Sometimes my ADHD is like, go, let me make the mistake first, then tell me how not to, and that's not good for these tutorials. I mean, it's fine. It's just, it does take some patience getting into this fucking thing. Hold on, I'm opening my shit. Where is my thing? We're finally getting into it. Oh my god. Nope, that's the wrong one. This one. I think it's... Oh, whoops, that's the wrong, I accidentally clicked the thing. There we go to here. Boom. All right, so let's see what else we have going on here.
Folder I have on my system where I am going to be storing my projects for this chapter. The first thing I am going to do is copy code from...
All right, what are we going to do, big man?
I am going to go in and copy things over, and I am going to put these in 4.2 number systems. I am going to open this folder in Visual Studio Code, so I am going to go to File, close the folder we have now, and I am going to open up a new one, open folder, and I am going to
bring in the freaking the copied thing.
I am going to open this project here that says number systems. We are going to get rid of the welcome screen and open our main CPP file. We're going to get rid of this const eval thing and clear everything we have in the main function here.
Okay, I should probably have this return 0. But I should probably save a version of this that's like completely empty, but I'm not. I'm lazy. Let's see.
First thing we want to do is to store an integer that is 15, and we're going to say int number 1.
Oh, whoops.
the exact same thing we had in the slides, and we're going to store 15 in this variable here. This is going to be represented in decimal, and if we want to store the same number in octal, we saw that in our slides we could store this as 017. So let's do that. We're going to say int number 2, and we're going to store in 017. This is not going to be 17. This is going to be a representation of a number in octal system. So we're going to say that this is octal, and we can represent the number in hexadecimal as well. So we're going to say int number 3, and it is going to be 0x because it is hexadecimal, and we're going to say 0f. This is how we represent it. You can use lowercase or uppercase, it won't really matter. Let's use uppercase here, and we can use binary because we are using C++20. So we're going to say int number 4, and we're going to store in a representation of 15 in binary, and it happens to be 4 zeros and 4 ones, and we have to prefix this with a 0b. This is how it works. So this is going to be in binary, and if we print all these numbers up, we're going to see, let me not tell you this, what do you think we'll see? Okay, so I went ahead and
he wrote out all the things. He wrote it all out instantly. That's fucked up, man. Hold on. I gotta catch up. Number 1. Number 1. Oh my god. We're finally getting to do something. Yeah. End line. Alright. So what we should be able to do is just copy this whole thing and then change the numbers. Change the number 1 and shit to the relevant values. So this should be 2, 3, 4, and 2, 3, 4. All right, let me make sure I'm not tripping. Is there any of this stuff that is not like not correct? So what it should do when we do that, when we build this and when we run it, what it should do is just print the number 15 4 times, I think. My streaming fear is making everything nice and dark, but accidentally clicking something in OBS that flashbangs everyone with my bright pink Kirby desktop wallpaper. That is, I mean, for me, it's not. I'm not worried about doing that because that seems like an issue on your part. I have flashbang scenes. I will flashbang you. All right, hold on. Let me try running this. Make sure see if I can I'm well, that's with Clang. Whoops. Oops. Hold on. Let me terminal, new terminal. Let me fix that. Run. No, whoops, terminal. Run task, and we want to do G++, because that's the one that we've been doing this whole time. So then we'll run this one, and it should just print the same thing. It should print the number 15 4 times in a row, I think. Look at that. Well, technically it wrote number 1, number 2, number 3, but the idea is the same. Let's just bring up the game window here. Booyah! Yeah. All right, sweet.
Typed this out. What do you think we will see when we build and run this program? Before we do that, we're going to open a terminal so that we see it here, and we're going to terminal, run task.
All right, we got a little bit ahead of Gakwaya Sensei here,
successful. Build finished successfully. We have our rooster program in here. We're going to click somewhere in this terminal, and our terminal is going to show up. If we do dir, you're going to see that our rooster program is here, and if we run it, I want you to take a moment and guess what we're going to see. Number 1, 15, and number 2, 15, and number 3, 15, and number 4, 15.
That's what we did.
The same number we are storing in these variables, but we are using a different representation that is going to be convenient depending on whatever it is we are doing. If it is more convenient to use binary, we're going to use binary. If it is more convenient to use hexadecimal, please do use hexadecimal.
I'm curious
But
when
the
it would be
representation
convenient to
of
use
this
any of
number
these that
in
aren't
memory
decimal.
is really going to be the same. I really want you to take some time and let this sink in, because you're going to see these things a lot of times in your career as a software developer. So please do yourself a favor
I mean,
and
he
make
says
sure
that,
you
but
really
what? But like,
understand this.
explain
Okay,
when.
this is really all we set out to do in this lecture, trying to make sense of the binary
Wait,
numbers we
that's
have
not
in
chapter
memory
3, is it?
and how
No
we
way.
transform
Okay,
between
no,
them and different
we still
forms
got a
of
little bit more to
data
go.
that is
Quite a
easily
bit more to go, I should say.
manipulable by humans. All data is represented by a bunch of grouped cells of zeros and ones. We have seen this. As the range of your data grows.
Yeah, so like binary makes perfect sense insofar as it is the language that the computer uses. Like hypothetically speaking, if you could like write directly a bunch of zeros and ones to the computer, you could tell it to do whatever the fuck it is that you're trying to do. But because that is an insane person's task, we try to do it in ways that our normal and human brains can understand, like with code, where we do this and then translate this to a bunch of zeros and ones. I wonder if we'd be able to. I I wonder. I wonder if it would be like. Is there? No, 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 no. I'm like, I'm fucking going insane here. This made me think of like, would a hypothetically like alien AI race be able to Would we be able to communicate with them using just binary? Would that be a thing? Would we need to use this shit to talk to them? Oh god, that would be insane.
So will be the number of digits you need to represent the data in memory. We have seen that the hexadecimal system makes it a little easier for humans to handle streams of data in ones and zeros.
Hexadecimal, I understand. I'm curious.
As hexadecimal, but it's almost
okay.
no
So it's
longer
just
used in
it's
modern
just
times.
archaic.
I just mentioned it here for completeness.
Okay, that makes
going to
sense.
stop here in this lecture.
I'm fine with that.
We're going to look at integers in a little more detail. So go ahead and finish up here and meet me there. In this lecture, we're going to learn a little more about integers in C++. Integers are represented by int in C++. It's what you see on the left here.
That's this thing.
And they are used to store whole numbers. Things
right?
like 1,
whole numbers.
2, and 3.
Miss Tron, when does the tutorial get easier? It does not.
In memory, but in most times it's going to be 4 bytes. So, for example, if you have a variable called age and it is an integer, this is how it's most probably going to look in memory. It's going to take 4 bytes. And I really want to make it clear what a variable is. It is a named piece of memory that you use to store specific types of data.
So, like so age is a variable as well then. And then like I'm not going to open them, but like we had a variable called sum before, right? That we printed like 6 different times as we changed it and as it became relevant. So, I mean, that makes sense.
Okay, so here if we have a variable named age, it is a named piece of memory. Age is going to be the name of that piece of memory, and we can store data in that memory. It's going to look like this in memory, but the value is going to be stored in here in binary format. I really hope this makes sense. A variable is a named piece of memory that we can use to store different kinds of data in. Okay, now we're going to look at a few examples of how you can work with integers in your C++ program. You can define a few variables. Here we have one that is going to store the number of elephants we have. You can declare it like this and not put in a value. And if you do it like this, the compiler is just going to put in some garbage value that is really not meaningful for your program. So you see the warning we have here. As a comment, the variable may contain random garbage value, And this is something you need to be aware of. Another way we can define integers in our C++ program is this statement here that declares a variable called lion count. It's going to initialize to 0. If we use curly braces like this, it's going to initialize to 0 by default. We can also explicitly put in a value. We can do the same with cat count, and we can use these variables to do operations. For example, we can declare another variable, and it is going to store the number of domesticated animals, and we're going to add up the numbers for dogs and cats. And
this feels like what we did on the first day, where we just did a bunch of addition and like learned how to add things together. But this was, I mean, but it wasn't as well, I guess it's a little bit different because it uses two other variables, right? Dog count and cat count. Well, we declare them here, but I guess, yeah, dog count 10 like this and cat count 15 like that makes it so that it's basically the same thing as equals this.
We're going to store the result of that in our variable that is called domesticated animals. This is something you can do. Another thing that can be problematic is trying to use variables that you haven't defined or declared in your program. That is going to give you a compiler error, and the compiler is basically going to say,
I think we did experience that when I first fucked it up.
I don't know what this doesn't exist to is. It is not defined anywhere in the program. Another thing you can do is try and store a fractional number in a variable that you declared as an integer. And this is going to give you a warning because fractional numbers are usually bigger in size than integers. And
that's actually, what if I just do like this? That should give me an error, right? Integer number 1, I have it set as 1.5. Because so why does it say double 1.5 when I go over it? Is it just automatically fixing it or something? It doesn't seem so. It's not giving me any sort of like warnings or error or anything for declaring it as an integer. Even though this should theoretically be wrong. Yes. So it's like it's automatically reading it as a double even though I've said integer.
Is going to lose some of your data. We don't really have enough tools to understand this now, but we are going to understand this a little later in the course. But this is something you can do. You can take a fractional number and store that in an integer variable. And we're going to do an example and see how this behaves.
You can do that
with our compiler, that is GCC 10. Okay, here we have mostly used curly braces to initialize our variables, but we can also use parentheses, and this is going to be.
Yeah, I think technically I could do like this, and it would be fine. This should be exactly the same thing as these other ones.
Usually referred to as functional variable initialization because we are using parentheses. And this is mostly going to do the same thing we saw in the last slide with curly braces. But when we come to the example here where we are storing a fractional number, this is going to silently chop off the data you have in a fractional number and turn that into an integer. And this.
Oh, wait, so if I do... So if I'm not using the curly braces, if I use a regular parentheses, is that maybe going to give me some sort of issue? It doesn't seem like it. It still says double. I guess it's...
This is called implicit conversions, but if we go to the last example here, where we are storing 2.9 into an integer, this is going to take this fractional number, chop off the decimal point, and only store 2 in this integer. And this might not be what you want, and it is going to happen silently, so this is a really bad way to do this. If you want...
okay. So... okay, so if I highlight if I mouse over the the parentheses, it's storing the integer of 1. It's correcting it. Yeah, and then if I have this, if I hover over the 1.5, it tells me what I should be doing. So it's correcting it. So if I do it now, if I do it as double, this should be yeah, okay. So this is octal, this is hex, this is binary, and this says decimal now. Okay, so now I have the correct value. Or I have the correct like it's reading it the way that I've intended it to be read. It seems.
Want
Okay.
to do something like this, it is preferable to use curly braces because you are either going to get a warning that this is going to lose you data, or you're going to get a compiler error and the compiler is going to completely stop you from doing this. And again, if any of this doesn't make any sense, we're going to go in Visual Studio Code, play with this, and see how the compiler behaves with these things. We have another way we can initialize our variables in C++. We can use assignment, and we have done this a couple
This is
of
what we did in the
times
beginning, I
course,
think,
but this is something
with
you can do,
x
and we are
equals
going to
whatever.
play
Not
with
x,
this
but
in Visual Studio Code
we
in a
declared
minute,
sum
and you're
equal
going
to
to see how it
whatever.
works. Okay, by now we have seen
Number
3
1
ways we
equal,
can
number 2
initialize
equal.
our integer variables. We can use braced initialization, which is basically using curly braces. We can use functional notation, which is using the parentheses, and we can use the assignment initialization, which is what we have here. Another thing I really want you to see is that it is possible to query for the size of your variable. Here we are trying to print the size an integer is going to take on our operating system and compiler. And if we try to run this on our compiler, it's going to tell us exactly how much memory an integer occupies in our program. We can either pass int explicitly like this, or we can pass a variable name, and it is going to work equally well.
So when we okay, actually that makes me curious. What if I do std cout and it should be size of number 1 boom, boom. And then I do size of, and if I do number 1 here, that should be, I mean, maybe we'll fuck with this later, but I'm kind of curious now, so. And then I can compare that to, because these other ones are all 15, so they should all theoretically take up the same amount of size and same amount of size, right? Or same amount of memory. Is kind of my guess. I don't actually know if that's true. We'll do 2 of these, I think. Size of number 2. Oh, wrong one. std and l. What am I doing? I could just copy this whole thing, paste it in, and we'll change this to 3. So theoretically, so these are all 15. This is 1.5. Here, let's run task. And then run it. Okay, so 2 and 3, the ones that we check the size of, are both 4 according to this. They're taking up 4, I guess, bits. I assume this is in bits. 1.5 is taking up 8. That's interesting. I'm craving pancakes, but I can't make any because I'm on that grind set. Hell yeah, dude. I want pancakes too, but I'm not on that grind set.
Okay, ints are mostly going to take up 4 bytes in your memory. So here we
That
have
makes
a
perfect sense.
representation of 3 ints in
Integers, yep.
memory. If we go from this 0 to this 0, this is going to be exactly 4 bytes. And this is how it may look in memory. One other thing I haven't really talked about on purpose is that there are a few rules you have to follow to name your variables in C++. One of those rules is that a variable must start with a letter like A, B, C, D up to Z or an underscore. You can't start a variable, for example, with a number. That's going to be a problem. After the first character in your variable name, you can really put in anything. You can put in numbers.
But the first value
you can really
has
put
to not be a
you
number.
want. But the first one can't be a number.
Okay.
Variable names are also case sensitive. So if you have a variable called
we've noticed that one already.
Lowercase b, and you have another one that starts with uppercase b,
that's a different
these are going
thing.
to be two different variables, and you have to be aware of this. No spaces or special characters are allowed in your variables. You can use underscores, but you can't use something like plus because that's going to be confusing to your compiler. And these are a few rules you really need to be aware of, and you're mostly going to be fine. The general form for
How can I become heiress if I fall for pancakes so easily?
Your variable is
you can't.
What you see here. You're going to pass the type. In this case, we have used int because we are learning about ints. You're going to pass the variable name, and you're going to put whatever it is you are initializing your variable with. Okay. Of course, this is braced initialization because Lee's using curly braces, but you can also use functional initialization or assignment initialization, and it is going to work equally well. Okay, now we have enough information to go in Visual Studio Code and play with us. Okay,
well, we've done a little bit of playing with it, but let's see what else we can play with it. Some things that I don't know about.
Hop over in my template project and copy the files.
Don't make fun of Gakwaya Sensei.
I'm going to go up again and go on the project that is called integer types. I am going to go in and paste in my files, and I am going to open up this folder in Visual Studio Code. I am going to close the welcome screen here and open my main CPP file. And I am going to do the usual, take out the things we don't need. To save on time, I am going to put in a piece of code that I have lying on my drive, and we're going to go through it to save on typing time. I don't want you to suffer watching me type this. The first thing we have is the elephant count. This is a variable that is not
So that's the one that was like junk,
so this is going
like
to
it just gets random data.
It's not going to contain
garbage
anything
data
that is useful to us. But some compilers are going to usefully put in a 0 because that's a logical number to put in here. If
when you haven't explicitly given something, 0 makes sense. So, but I guess G++ doesn't do that.
And this is going to automatically initialize.
So if we add the braces, it initializes to 0.
Explicitly initialized with a 10. And the cat count is going to be initialized with
those
15.
Two are initialized.
You can try and print these out and see what you come up with after compiling this application.
That's actually a good question. I think so. Okay, let's put this in. Let's go in and let's go in and check out what the at least what the elephant count one does. So int elephant count, and this one is just nothing. So then int lion. I keep putting spaces. Lion count. And then this one initialized like that. So int dog count. And then this one at 10. And then int cat count initialized at 15. So this one should be, we're gonna do a little bit of well, officializing my guesses. We'll do fucking garbage value. So garbage value value of 0 and values in braces. We'll just do it like that. Let's separate these a little bit. Just so that actually, I don't think I need to be quite that far. But like this should be good. Yeah, that looks neat.
Another thing we have seen is that we can do something like this and put an expression into our curly braces, and the value this evaluates to is going to initialize this domesticated animals variable.
Yeah,
and
that makes
now
sense.
you should know that this is probably going to take 4 bytes in memory because it is an integer. This is really how C++ works. Each fundamental type has a size associated to it most times. So integers is mostly going to be 4 bytes on your system. And we're going to query this a little later in this video.
So he says that it's mostly going to be 4 bytes. Is that is it like if I get a really big integer, is that going to give me a much larger thing? Oops. Cat count. Like if I make my fucking if I make my if I create an integer that's like fucking ridiculously large, is that going to ooh, an error. Integer constant is too large. I guess it will. I guess it does cause problems. I'm sure that
Okay, let's try and compile this program and see if it actually works.
If you throw the integer in the bin, it's a binteger.
The build is successful. Another thing we can do is try and use variables we haven't really declared in our program. And you can guess what is going to happen. If we try
this one we've tried before and it just doesn't compile because it doesn't work, right?
Put in doesn't exist. You know, it's a number that doesn't exist. The compiler is not going to know what this is because we didn't declare a variable.
We didn't declare doesn't exist.
If you try to compile this, you're going to get a problem. You see that we have a problem before we even compile. So Visual Studio Code is this smart. It can analyze our code before we compile it and give us hints to problems that might come up. You see here it is saying doesn't exist isn't defined. So if we try to compile this, we're going to get an error that we expect. It's going to say doesn't exist, doesn't really exist. I don't know what that is. So you shouldn't really do that. You shouldn't try to use variables you have.
Everything that you've created needs to be everything that you use needs to have already been previously created.
Initialization, as we have seen. Okay, another thing we can do is store a fractional number in an int variable, and we're going to see what this does. We're going to try and
this we didn't actually do. Also, I can't help but notice that, at least as of yet, he hasn't created anything to print all of these values out. So we don't actually know. If we run it, it's not gonna show us anything. I'm sure he'll do that before conversion. And this was, he has this at 2.9.
compile this code, you see we have a 2.9. We're trying to store this in an integer. If we try to compile this, let's try and use GCC. Let's clear this. Let's bring up a terminal and try to build this. We're going to try and run our GCC compiler on this program. It is going to say error narrowing conversion of 2.
Oh, hold on. I want to see. I want to run task. G++, and it should give us narrowing conversion. Narrowing conversion of 2.89 times fucking however many e plus 0 from double to int.
0.899 from double to integer. C++20 isn't even going to allow this. So this is a good thing.
It just straight up doesn't work.
You might think that you have a 2.9 and some compilers are going to chop this off and store a 2 instead. So this is one of the safe things about this way of doing things. So I am going to comment this out because otherwise our program wouldn't compile. Now that we know how to use these things, we can try to print the values in here. Okay, I am going to put in a piece of code I have lying around.
Oh God. Okay, so he is going to do all that. So I'm just gonna get rid of this instead of commenting it because I don't see a reason to keep it. Solipsist try to type hello world and it errors because world isn't because world doesn't exist. Oh God. All right, let's do our std cout. Oh wait, that's right. Elephant count. Elephant. Ooh, elephant count and std and l. Right. Wait, am I tripping? Clear. Oh wait, what am I doing? Oh, it's still thinking that I have that, but I've deleted it, so I'm not concerned. So we got that. And this one should be, so there's lion, dog, and cat. Do lion count, dog count, cat count, dog, cat. He's put extra lines in between, I guess for readability. It's not an elephant, it's a it's a heffalump snuffleupagus. No. No, I won't. Alright, so the elephant count should be a random value, if it even works. Which I don't think it will, but it might. Yeah, and we don't have this thing anymore. So, terminal, run task. Alright, so this one built properly. So let's run it. Elephant count 1. Interesting. Okay. So I was expecting the garbage value to just do like random numbers, kind of like I think Lazy gave me a thing that would it accessed like a random part of memory every time, and it would it would give me a different like I don't remember exactly how long it was, but it would give me a pretty long number every single time that I accessed it, and it would be different every time, like not even close to each other. The fact that elephant count is just 1 here indicates to me that this garbage value, I mean, the fact that it's going to be the same every time is one thing. I'm curious as to why that would be. It just says garbage value when I mouse over it. Value of 0. So garbage value being 1 is something, I guess. That's interesting. I don't know why that is. Maybe he'll explain it. Let's
Around on my drive, I am going to remove these spaces inside because it is annoying. Let's
Oh.
do this. And if we try and build this program, it
I
should
also
compile successfully.
I
And
didn't do
if
the
we run it,
domesticated
we
animal
should
count
see
either.
our numbers. We're going to go in our terminal here and do dir, and we're going to run rooster. And we're going to see elephant count is 1.
So we don't have the 25 at the end.
This is a garbage value, so it could really be anything. Lion count should be 0. Dog count should be 10. Cat count should be 15. It is what we have.
Yeah, and then domesticated is just adding these
animal
two.
count is 25 because we have dog count and we add that to cat count, and we're going to end up with 25. This is what we expect. Now that we know how to work with this, we can also try and play with functional initialization. Before I put in my code, I am going to comment all this out because I don't want this to disturb us as we work with our functional initialization code. So I am going to comment all this out. And
okay, so let's so all of this should be fine. I think it's funny. So I guess not that funny, but it is kind of interesting to me that what he mentioned before, I think on our last one, is that you can't nest like block comments like this, but the fact that you can't do that, but you can just have random comments inside of it, I think is kind of funny, kind of amusing. Dog count. Tara. At a wildlife reserve once, I saw a baby elephant try to walk up a cliff and fell down, and then it did it again and fell down and got confused. I mean, there's no accounting for... It's got the spirit, I guess.
and go all the way down and put in my code for functional initialization.
Okay.
And you see here we have a variable called apple. We initialize this to 5. We have orange count, which is 10. We have fruit count. And we have a bad initialization that is not going to work. It doesn't exist. 3 and doesn't exist. 4 don't really exist. So this is going to give us a compiler error. And if we do something like we do in narrowing conversion functional here, this is mostly going to compile. And this is going to chop off data and store a 2 instead of the 2.9. This is something you should really be aware of. And you see the comment here says information lost. This is less safe than braced initializer because braced initializer is going to give you a compiler error if you try to do this, and that's a good thing. So we also try and...
Whoa, hold on.
Compile.
So this is our functional initialization. This is our... So he included a bad initialization commented out there, but that one we already know that won't let it compile because it's 2 numbers that don't exist. And then this one, information lost, less safe than braced initialization, I think is what it says. And then this one is that's the narrowing conversion.
Error if you try to do this, and that's a good thing. So we also...
Less safe than braced initializers. There we go.
Also try and print these out, so I am going to tidy this up a little bit, and I am going to try and compile this.
Yeah, I'm gonna go ahead and copy this and change the things. So this one will do, it was apple count, boom, boom, and then this one will be Oragna Joe. It's orange count and fruit count. The word count looks fucking fake. I don't know why. I need to code my own real Waddle Dee. Nice.
Piece of code, run task and
Isn't
build
the
with
narrowing...
GCC. The build is going to...
Ooh, okay, wait, hold on. The narrowing function conversion one did work, so let me put that back in. Less safe than braced initializers. And then this one is int narrowing conversion functional 2.9. So this one, the fact that we've stored this as an integer, I'm kind of curious what it's going to do. Because he's created something here for it to come out, or to print conversion. And this one is narrowing conversion functional, std and l. And the fact that it built, the fact that it actually built has me kind of curious. Terminal, run task, G++. It built. Let's run this. Narrowing conversion 2. So we have our apple count 5, orange count 10, fruit count 15, as expected. All that stuff makes sense. And the narrowing conversion is 2. So it completely cuts off the 0.9 here. Let me see. If I do std cout, boom boom, size of narrowing conversion. Oh, I also don't put out, I didn't have a space here. And then I do size of, I think it was this one. I think that's how it's written. I'm sure Visual Studio Code will tell me if I'm fucking this up entirely. It says it's expecting a semicolon. Here, let's see if size of narrowing conversion int main. So in function int main, error expected a semicolon before size of. What, just here? That doesn't make sense to me. Oh, is it on the last line? No, it's not. Okay, we're gonna get rid of this line for now. I'm gonna put it on my thing. Yeah, so the size of is gone. I kind of wanted to see whether it was storing the size of this one as being more than 4.
Pass through without a problem. And if we do clear and run rooster, we're going to see apple count is 5, which is what we have in here. Orange count is going to be 10, so this is right. Fruit count is going to be 15 because it is 5 plus 10. And what is really worrying is that narrowing conversion is 2, but we didn't store in a 2. We stored in a 2.9.
Right.
And because an integer can really store 4 bytes, 2.9 is more than 4 bytes. And it is going to store what it can, and it is going to...
Okay, so that actually makes sense. The way that it was just explained actually makes perfect sense. So because we're using these braces instead of the other ones, and we've stored it as an integer, it completely gets rid of the 0.9 because that's another 4 bytes of data. So, but because it doesn't have that much to store in integer, as an integer, it doesn't have enough data assigned to it essentially. So it stores what it's capable of, which would be the 2, which would I think be just 0 1 0 0, or right to left 0 1 0 0, but 0 0 1 0 is the It'd be 2.
To chop off this 2.9 and only store in a 2. So this is
So
really something you should be.
So that actually answers my question already, because the size of that I had before would have given me a value of would have just given me a value of 4.
Aware of. Sometimes this is going to cause problems in your program, and really, if you are trying to store fractional numbers in an integer, please use a braced initialization form, because the compiler is going to stop you from doing this if you try. Okay, so this is really the difference between functional notation and braced initializer notation. Functional notation is not going to give you an error if you try to store something that can't really fit in a net. It is going to silently chop it off and put in whatever it can. And braced initializer is going to give you a compiler error. So this is the difference between these two. Okay,
Yeah,
I am going to comment this out as well. And I am going to put the starting comment here. And I am going to go down and show you that you can do assignment initialization as well. I am going to put in my code here because I don't want to type it really, and I am going to print all this out. And we have a bike count variable that we initialize using the assignment notation. Truck count is going to be 7, vehicle count is going to be bike count plus truck count, and we're going to be narrowing conversion here, and we're going to see if this actually works. We're going to try and build
it should
this.
work, right?
We're going to run the task to build with G.
Well, let's get our shit to be the same. Assignment, notation. This is the same. This is functionally the same kind of thing that we've been doing up here. The difference is, okay. So this whole section is braced initialization, and then this is functional initialization, which, so like these are functions, these are braces, and then this would be, this is assignment. It's notation. He uses notation here, but I think it's probably the same. It's the same idea as initialization. So int bike count equals 2. Int truck count equals 7. Int vehicle count equals bike count plus truck count. Int narrowing conversion, oh, there's 2 R's. Conversion assignment equals 2.9. I'm in that awkward phase of Japanese where my grammar is mostly good, but it's just the endless vocab to learn. Vocab is, fortunately, when you have a good assignment of grammar, vocab tends to be the issue. But grammar can be confusing as shit sometimes in any language. So std cout bike count bike. Oh, whoops! I forgot to bike count. For some reason, I always see that as backwards. Bike count std and line. Yeah. I will say one thing. Truck vehicle. I will appreciate that this is very easy to just do, because you can just some of these early, at least these early ones, it's pretty easy to just put your, to just print the same thing over and over again. All right, so all of this should be fine, right? Truck-kun. Toraku-kun.
GCC, it is going to pass through. You can guess what we're going to see if we run.
I'm actually kind of curious. Does it have a run task? Only true Chads become Truck-kun. Wasn't there like a one-shot that where the whole point was the guy was a truck driver, but he was like trying to get unwitting heroes from our world to the whatever fantasy world needs them? So let's clear this real quick. So bike count is 2, truck count is 7, this one is 9, and then this one, again, because it's an integer, and because it's not, because it doesn't have enough data to store the whole value, it's only printing it as 2. That makes perfect sense. I like that.
Run the program. Bike count is 2, truck count is 7, which is what we expect. Vehicle count is 9, and the narrowing conversion is also chopping off what we have here. So this is something you need
Or
to
you
be
could inhale
careful
the truck.
about.
What am I,
Another
Kirby?
thing I want you to see is that you can check the size of your variables in memory. So we're going to check the size.
Oh, is this what I was trying to do?
And
Check
I'm going to put in a piece of code to really play with this. I don't want to type all this because it's really self-explanatory by now.
We need to do, okay, std. Wait, hold on. Can I just do this? Std cout. Size of int, and it was, how did I fuck with this? I fucked this up. Size of, oh, is it because I didn't do this I did this completely wrong. I don't remember exactly what I typed, but it was wrong, whatever it was. You didn't add, yeah, I didn't add the back one, or the things. I fucked it up. That makes perfect sense now. It's size of int. I think this one, it was gonna be, it was byte count, and then this thing. I think I was gonna do it 3 times, and it was gonna be size of bike count, size of truck count. I don't think this one was going to be size of narrowing conversion. So I'll do truck count, and this one is narrowing conversion assignment. So this, if I had to guess, because of the way that this printed initially, I'm gonna guess that all of these values are 4, because if the bike and truck, the bike and truck count should both be 4. The vehicle count should be 4. I'm not checking it because I'm like 100% on that one. This one should also be 4, even though because it only stored the 2, right? It didn't actually it didn't actually do the whole thing.
Print size of int, and inside we're going to say size of int, and this is going to give us how much memory is really occupied by an int. And we can use this form here by passing in a variable name. Track count is a variable we have declared and initialized here. So if we build
4
this
bytes of memory.
program, let's do that with GCC. The build is going to pass through, and if we run Rooster, we're going to see that the size of int is 4. You're going to see that this is in bytes. And
okay, so again, byte count, truck count, vehicle count, narrowing conversion 2792, and then size of, for all, not for all, but for 3 of the 4 values that we checked, all of them are 4. Okay, that makes perfect sense. I am understanding things. There's one piece of forgotten land we haven't stepped on. Your face, failboat.
Size of track count is 4 as well, because track count is also an integer.
Yep.
So these are
that
all
makes
little
sense.
tools you can really use to know how much memory is really being used and occupied by your program. And this is really all we set out to do in this lecture, to learn as much as we can about integers. Integers occupy 4 bytes in memory for the most part, and we have seen different ways we can initialize our integer variables. We can use
all these
braced
different ways.
initializers,
I think braced
which is going to
initializers are
use
probably the
curly
ones that
braces.
are most
We can
useful,
do functional initialization using parentheses like
I mean, I guess
this.
they all have
We
their
can
place.
also do assignment notation using a from like this, and we can use size of to check the size of our integer variable.
What I think is funny about the assignment notation, when we covered this in the we used this in like the very beginning. I said, or I not I said that during this whole section, with your first program and shit like that, because it was talking about we used. I could open it up, but it seems like a bit of a pain in the ass. But we did like we used like sum and stuff like that instead of just byte count, and we like learned to create an addition function, right? And later we did a multiplication function as well. But we used instead of doing it like doing it in this way, instead we kind of created. We used a function, and then we used the function to just print directly. We put the function in here, essentially, with the value, with whatever relevant values we had. But I guess that, I suppose this actually makes sense here, because we wouldn't be using a function to create these. Or at least a function wouldn't make this any more, this amount of code any more any smaller. The vehicle count maybe could be turned into a function, and then that way we don't have to change things. Like, or we don't have, not even then. I don't think this would matter, because we're only doing these two. Maybe if we created, if vehicle count was something more dynamic, it'd have to be changed.
I have to say that these kinds of initialization also work on other variables, but we took the chance to introduce all these concepts using integers. This is really all we set out to do in this lecture. I hope you found it interesting.
I certainly
did. We're going
did.
to stop here in this lecture. In the next one, we're going to start and learn about integer modifiers. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about integer modifiers. And these are little things you can sprinkle around your integer types to modify their behavior a little bit. But before we dive deep into this, let's talk about how
negative
we can
numbers.
Store positive or
because negative numbers would take more.
And we can do something like this. If we put
wouldn't they take more data
inside our value1 variable, which is an integer, it's going to work. We can also put in a negative number like minus 300, and it is going to work. So what's the magic here? Well, this is signed by default, and this is a modifier we can apply to.
So if we use integer, it's a signed integer by default. So if we change this to signed integer, if we change does that? I guess signed integer, like by default, it's like it assumes it's a positive one unless you put a negative one in front of it. Is there any reason to make it unsigned?
To our variable to signal that we have the possibility to store in negative or positive numbers, and it is going to work. If you only want to store positive numbers in your int variables, you can use another modifier called unsigned. And if you put in a negative number, you're going to get a compiler error. We're going to see how this works in a minute. Okay, regardless of whether your integer variables are unsigned or signed, they are going to still occupy 4 bytes in memory. So this is how it's going to look in memory. And here is a simple formula we can use to come up with the range of values we can store in our int values if they are unsigned or signed. If the
Wait a second. So he actually mentioned this formula before when talking about the number of the values that we can assign in binary like at all. And it's like we're for any value or for any number of digits n, it's 2n minus 1 is the maximum number of is the maximum number that we can get in decimal to represent it. But this is the actual thing then, isn't it? Because it's negative, because it also has the negative 2n. Negative 2n, negative to the 2n minus 1. I'm not familiar with this operator. 2n minus 1. Minus 1? What the fuck?
the number is unsigned, you can use this unsigned range formula and plug in the number of bits you have in your data type. If you are using a signed integer, this is what you're going to use. And here is a simple example. For example, if we have an unsigned int, this is the range of values we can store. We can basically go from 0 all the way to 4 billion.
It's the range of the function. Yeah. Yeah, I put that together as soon as I saw this this thing. That makes that's I'm no longer confused. It seems like though with an unsigned integer, it has the same total range. It's just only in the positive direction versus a signed integer can do the same amount. It's the same amount but positive or negative. So that's interesting. I guess that makes sense because that's the range. That's how many. That it has to do with the number of bytes in memory.
If the number is signed, the range is going to basically be divided into half. The half is going to go on the left and store negative numbers, and the other half is going to go to the right and store positive numbers. And you can see that we can basically go from minus 2 billion to 2 billion if the number is signed. Okay, by now we have seen two modifiers, unsigned and signed, but there are others. For example, you can flag your integer types as short or long. What does this do? Well, this is a table that I put together to try and come up with all the combinations you can come up with. If you have a short variable, it is going to be 2 bytes in memory. This is the modification that this modifier does to your type. If you have short int, it's going to be 2 bytes. If you have signed short int, it's going to be 2 bytes. If you have unsigned short int, it's going to be 2 bytes. You can see that the effect of short is really shortening the original size in memory for whatever type you applied this on. This is really working on an integer, even if we don't specify
is this like a form of
here.
compression?
For example, short here, it's going to implicitly be int. That's why we have 2 bytes, because it's basically an int that we have split in 2. Here in the second column we have int, which is going to be 4 bytes. If it is assigned int, it's going to be 4 bytes. This is really the sizes you're going to come up with if you use these combinations of modifiers on your integer types. One thing I really want you to be careful about.
Hold on. I need to look at that again. So we have our short. This is like the normal one. We have a long. The fuck is a long? Why would you want a long? So long integer, signed long integer, unsigned long integer. What does this do? This seems like a kind of compression. I don't know if that's the case. I don't know if that's why it would be used. Because if that is why it's used, then that makes sense. 2 longs don't make a right. Oh my god. Shut the fuck up, Tara. And then this one, integer. This is the normal one. This is what we learned. increases the range. So if I do, real quick, if I do, I'm just gonna comment this out because fucking, oh, whoops, wrong way. So if I do like, if I do int, and I have it as just fucking random number, and I just do this as, if I do it really long, okay, constant is too large. So if I do long, does that suddenly make it go away? Is that like the... no, our integer constant is too large still. Long? It still says it's too large. Okay. Okay, so it doesn't do what I thought it might do. When we say increases the range, what exactly does that mean? Add int? Oh, long int. Does the computer think 3 inches is normal or long? I'm sure that there's a value. Oh, I was like one thing to... Okay, so this works with unsigned long. Okay, so then if I just make it long once, is that suddenly too long again? Try unsigned long int. Unsigned long int. Oh, wait, what the hell? What is this? That's not a number at the end of it. 1515. There's like the number that I wrote in, and then it's after that it's UI64. So that, I guess that's long. This is the long int part. But also on all of his, he's got the same values on these kinds of things versus on the signed and unsigned. Hmm. I'm curious why one would choose to do something like this. Alright. But if I just set this one as integer, does this number work? It looks like it's correcting it automatically to unsigned long. Because as an integer, it's storing, it looks like 4822414459. I think this is like the highest amount. But then if I... That actually, okay. Because this is probably the most that it can store as an integer. This is probably the highest amount of data that it can do. Or highest amount that it can do with the amount of data that I've assigned it. Signed has to allocate 2 bytes of its memory to negative number, while unsigned allocates all of its memory to positive number. Okay. That makes sense. And then long increases the amount of data that an integer can be assigned, right? And then I guess if the number is big enough, it kind of... Wait, does that mean I mean, this might sound like kind of obvious, but this this makes me think that the amount of negative numbers that we can assign is like half the amount of positive numbers we can assign, because it just takes more data to assign a negative number than a positive one. Because it needs to allocate data to the negativing symbol, or negativing whatever the hell it is. I forget exactly what to call it. No, it doesn't take more, it takes the same memory. So, wait, hold on. Is it... but when we saw the ranges that it had available, it was like, when we see the ranges here, it says, like, we have, it is, for a signed integer, we can do this, and then an unsigned integer, we can go up to here. Is there a way to go to a negative value equal to the highest unsigned integer here? At least, like I'm sure, like, I just don't understand. I don't understand how exactly it works. Like, with a signed integer, it's the same amount of data both ways, or the same amount in either direction on the number line. But unsigned integers, be, it seems like it can go all the way up to, it goes much higher than the highest on a signed integer. Skipped backwards quite a bit to get back to this thing.
It's going to be 2 bytes. If you have signed short int, it's going to be 2 bytes. If you have unsigned short int, it's going to be 2 bytes. You can see that the effect of short is really shortening the original size in memory for whatever type you applied this on. This is really working on an integer, even if we don't specify int here. For example, short here, it's going to implicitly be int. That's why we have 2 bytes, because it's basically an int that we have split in 2. Here in the second column we have int, which is going to be 4 bytes. If it is assigned int, it's going to be 4 bytes. This is really the sizes you're going to come up with if you use these combinations of modifiers on your integer types. One thing I really want you...
Yeah, and then so with the longs, it was 4 or 8 bytes. It looks like that worked for either way, and then long was always 8 bytes, so it took more data.
To be careful about is that these
Or more,
modifiers
it
only work
will
for
take 8
integral
bytes.
types. So they work for data types in which you can store decimal or whole numbers. You can't use this on types in which you can store fractional numbers like 2.9. That's going to give you a compiler error. Now,
okay, so this is only for integers then. Like, it doesn't actually work for anything else.
Now that you have an idea about this, why don't we go in Visual Studio Code and actually play with us? Okay, here we are in our folder that contains our projects. We're going to do the usual and...
Yeah, he calls it projects, but I mean, most of this stuff I'm not super concerned with keeping. Actually, this might be worth holding on to just because of the size of stuff. Let me save this real quick. Let me make another one. Save this. Hold on, I gotta open up new shit. Project 4. Oops, that's not the button I wanted to press. File. Close folder. Open folder. It'll be... It's here somewhere. VS Code. There we go. Alright.
And copy the files from our template project, and we're going to put those files in our integer modifiers project here. Let's open it up and paste in the files. We're going to go up again, and we're going to open this up in Visual Studio Code. The first thing I want to play with is storing positive and negative numbers in our integer types. So we're going to say int value 1, and we're going to store in a 10, for example, and we're going to do int value 2, and we're going to put in a minus 300. I think this is what we had in our slides, so we're going to keep this. If we try to print this out, so we're going to say value 1, and we're going to say value 2, and we're going to try and build this. So we're going to open our terminal so that we can play with it right away. And we're going to run the task to build with GCC. The build is going to be successful. If we run our program, we're going to see that it's going to say value 1 is 10 and value 2 is minus 300. This is really cool. We can store positive numbers and negative numbers in our int types. And this is going to occupy 4 bytes in memory. We can prove this by printing the size of value 1 and value 2. Let's do that. So we're going to say size of value 1 is size of value 1. We can also do it for value 2, size of value 2, and it's going to be size of value 2, stdendl. If we build this again, we're going to run the task to build with GCC, and we run our application. It's going to say 4 bytes. So it doesn't really matter if we store in a positive number or a negative number. It's going to be 4 bytes. This is the point I want to make here.
Okay. And so that makes sense. It says that it's... So they both store 4 bytes. Wow, I gotta make sure I get... I want to see all of this. Size of... value 1. And this one is going to be value 2. Oh, I gotta pull up a new terminal. Shit, I always forget to do that. Okay. So now we have our shit all the same as his, from what I can tell.
Another thing you can do is actually make it very clear that you have signed numbers in here, and you can use the signed integer modifier here. So this is going to give us the same result. And if we try to build again, run the task to build with GCC, the build is going to be successful. If we run the program, we're going to get the same result. So if you don't put a signed, or if you put it here, it's going to be exactly the same thing.
So int is signed by default. Look out, it's hot wizard code violation. Oh god. How you doing, Steve?
Another thing you can do is make it very clear that you want to store positive numbers in your variables. We can do that by using the unsigned integer modifier. So we're going to say unsigned int value 3, for example, and we're going to put in a 4. This is going to be fine. But if you do unsigned int value 4 and put in a -5, for example, this is going to give you a compiler error. because you said this is unsigned, and this really means that you want to store in only positive numbers, but you are trying to put in a negative number. If you try to build this, let's try this. We're going to run the task to build with GCC. We are going to get a compiler error saying conversion from minus.
Okay, well, let's get that error real quick. Run task, and it should be okay. I'm okay-ish. Been outside 3D scanning car for, or at least trying. Damn, trying to 3D scan a whole car. You planning to like download a car, like those fucking those old advertisements? It'd be like, you wouldn't download a car, but like I would totally download a car though.
-5 to int. This is not allowed. You're going to get a compiler error. Your program is not going to compile.
Yeah,
so
it definitely didn't compile.
Error. Let's say this here. And this is really all I had to share about these signed and unsigned modifiers. Signed is...
I mean, this makes sense. Compiler error. Boop boop. Everyone would download a car. I mean, yeah, everyone would download a car. I always thought those ads were silly. I didn't even understand what they were supposed to be for. It was like, oh yeah, don't like pirate stuff. But then like as I got older, I was like, wow, these companies really suck ass. I'm gonna pirate their stuff. Not that you should. It's against the law. It's illegal. Don't do it. That's why I'm using free resources to learn to code.
Is going to mean that you can store negative and positive numbers. Unsigned is going to mean that you can only put in positive
The ads were never
numbers.
active in the UK, but the idea seems stupid.
Number, you're going to get a compiler error. Now that this is commented out, if you try to run the task to build with GCC, the build is going to be good.
You can use /n instead of std_l. I did actually that was actually explained to me. I think it was like this /n. I forget exactly how it was done. And then get rid of this. No. Unrecognized token. I don't remember how to do it. But it was explained to me that it was doable before. What the guy who explained it to me was like, I hate this, it's ugly, don't do it. It is technically shorter, it's fewer characters.
And we will be able to run our
How am I getting on? I'm enjoying it.
To do whatever it was doing before, as we see here. We also saw that we could use the short and long modifiers, and we're going to put a piece of code here that is going to allow us to play with them.
Oh god, it's the code that he wrote in before.
And if you don't want to type this as well, you can get this code from the resource section. It's going to be linked. You get
yeah, it might be linked in the original video, but it is not linked in this version. Short and long. So let's short. Wait, what am I doing? I'm just gonna get rid of this thing. Short and long. I won't annoy you too much. I don't understand C++ that well. Oh, don't worry. I don't understand it either. That's why I'm here. Fuck is this? Why is it giving me some... What is this error? The fuck is this? Yeah, no, I don't care about that. Short and long. Oh god, I'm like all fucked up and don't know what I'm doing. Alright. Short variable. -32768. I don't know if that actually matters. So this one says 2 bytes. So all of these are supposed to be 2 bytes, right? Because they're all short integers. 455. signed short, signed short 122. We're gonna get our shit all. We're gonna look exactly the same as him. Okay, that's what we're gonna do. Signed short int. Signed short int minus 456. Unsigned short int. Unsigned short int. Oh, I gotta int. Oh my gosh. And 456. So unsigned's always positive. I don't know about him, but most normal people use /n. Let's see.
You can open the link, use the code, copy the code and paste it in here and really play with it, because the point is really not to type all this. The point is to understand what these modifiers do to your variables. What we are going to do, we're going to try to print them out and print the size they actually have in memory. We're going to do this in 4 groups. We're going to do one for short and long. We're going to do one for int here. We're going to do one for long. And we're going to do one for long. These are things.
Okay, so we don't need to do the int ones. We did the int ones last time. We can do, I think we can bother with the long ones though, because longs were different than the ones that we initially did. This is 4 or 8 bytes. Long int 33. Signed long 44. Signed long int. Signed long int 44. Unsigned long int. Unsigned long int 44. And then this is the longs. Long 888. And this is 8 bytes. I forgot my little long int. Long int. I think long int 999. Long no, this one's supposed to be signed long. Signed long signed long 444. Signed long int. Signed long int. I probably could have just gone and found whatever he was talking about, but it's not linked in this video because it's the really long one. But it is unsigned long int. I'm sure it's very helpful on the original one though.
Things you can do, and we're going to see how much memory is actually being used by all these variables. We are going to start with the first group here. So we're going to go down and print the sizes out.
Yeah, I think I'm going to do the prints right under for each one underneath each thing. cout. I think it's that one. Size of short.
And this may.
Oh my god. Okay. Okay, so we're gonna. He has two different ones, one for the size of and one for the actually printing the variable or the integer, I guess. Oh fuck me, dude.
May be really hard to wrap your brain around, but they are plain old std cout statements that we have been doing all along. I am going to split this on different lines so that you can really see this. So we have.
Okay, so he's got short variable, size of. Oh my gosh. So, short variable. And this is short variable. He's done this all confusing like for me. Size, and then it's size of short bytes. All these, I mean, I'm complaining about it. STD. I'm complaining about it, but it is functionally just. So I come here. It was 5 different ones. So short variable, and this one is changed with each of them. So it's short int, and then this one has the size of, and it's supposed to be. I guess this one's supposed to be short int. Yep, that one's short int, and then this one is signed short. And this one is signed short int. And this one is unsigned short int. At the very least, so signed short int. Oh, so this one's supposed to be signed short. This one is signed short int. And this one is unsigned short int. Right? Am I missing anything? So all of this. My god. This is a goddamn nightmare. It's not that bad, but I'm going to complain about how long this is. And I think that's why he's shortened it on the video. I say shortened, but he's like put it onto 2 lines. But I hate that. This was so difficult to parse at first. I'm just gonna leave mine on 1 line for each of them.
An output statement for a short var, which is what we have here. So we expect this to take 2 bytes, and all these things are probably going to take 2 bytes. Let's try and build the program with GCC.
All right. Run task, G++. All right, well, built properly.
See, the build is going to be successful. We are going to run rooster, and you're going to see that short int is 2 bytes, signed short is 2 bytes, and everything is basically 2 bytes in this group here. And we did guess right. The next thing we want to try out is...
So all of these are 2 bytes. I'm curious how that works. What does the binary look like? Like just how? I really don't understand how that works. Because the way that he explained it before with the binary was that it was like each byte represents a different like a little bit of data. So it makes sense to me that like I guess it also makes me wonder how they represent larger numbers. Because with 2 bytes, I would imagine I keep trying to click only the 2, but I imagine that you would only be able to represent essentially maybe 3 total numbers, right? Because it would be, or 4. It'd be 0 for 0, 0, 1 for 0, 1, 3 or 2 with 1 0, and then 3 with 1 1. So that's 4 different numbers with 2 bytes. But I don't know how do you represent this in only 2 bytes? Negative 32,768. 2 bytes is 16 bits. Ow! Oh god, I'm like getting my terms all fucked up. 16 bits. Even then though, how is it 16 bits? The fucking it was with I guess that makes more sense. Yeah, that actually is a complete that's just me not knowing what the fuck I'm talking about. Even though he just explained it. Negative 32,678. I'm curious how negative is represented in binary. Do you happen to know that? Because like how would you? I guess it would be like if it would as a signed integer or something. I guess that you would assign one of the bits to be equal to positive or negative, and then that bit being one or the other would kind of it would take up the same amount of data as the unsigned integer, and then if it was or as the yeah, I can't words good. I think I understand it. Like fucking can I open I should have a notepad, right? It's called two's complement and it's a bit different than that. Hmm. Is there is there any chance that that'll get covered in this course? Oh god, I'm so confused. I'm confused with how the numbers work and how it all is read by the thing. Like functionally I understand. Ooh, that's tinnitus. That's interesting. That hasn't happened in a while. Uh, functionally I understand that this works. Like this takes 4 or 8 bytes of data. This takes 8 bytes of data. Uh, this takes 2 bytes of data. I understand that it works. I'm curious how all it functions on, I guess, at the computer's level. All right. Don't bother with binary. Let's see. So let's do this. We'll do long variable, long, long, long. long. And then I'm going to change all of this to long var long int signed long signed long int. Wow, that's not what I wanted. And this one should be unsigned long int. long int, and this one is signed long int, or no, signed long, and then this one is signed long int, and unsigned long int. There we go. This should also run just fine, hopefully, unless I fucked something up. Clear. So these are all 4 bytes by the looks of it. I didn't actually print the... Ah, well. These are all fucking pointless. So all of these are still 8. I'm curious if... So this says 4 or 8 bytes. Does that mean I can just store even longer values in them? Because none of these were 8.
Is this group of ints. So we are going to go down and give ourselves some breathing room, and we're going to paste this in, and we're going to separate these again so that we can see what is really happening here. And I think this is really enough. So we're going to see the sizes for the things we have in this group here, and we expect this to take 4 bytes. So let's try and run the
those
build
we
task
saw
to build
before
with GCC. The build
that
is going
regular
to be
integers
good.
are just
We
4
can run the
bytes.
program like we usually do, and you're going to see that int variable is 4 bytes, and everything in that group is 4 bytes. And this tells you that regardless of the signed and unsigned modifiers you put here, it's going to really use the size of int here. Okay, it's going to take 4 bytes in memory. Let's try this group here. We are going to go down and put in the code to print the sizes for them. And this is what we should use. Let's split this on different lines so that it is easier on the eyes. And again, if you don't really want to type this, you can get the code from the linked resource section. You're going to find the code here, and you can copy and paste and really play with this. But it is helpful to really type these things out and really bring these things in muscle memory, because it's going to help. Okay, so we have this in. We're going to try and run the build task with GCC. The build is good. We're going to go in here and run rooster, and it is going to say long variable is 4 bytes, and everything in this group is basically going to be 4 bytes in here. The last one is this long thing.
Why?
It is going to really give you a huge range for your values you can store in the variable, but don't really trust my world. Let's try this out so that you can see for yourself.
Oh god, I have to do the fucking longs too. God damn it. Okay. Well, let's do this. long, 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 long variables. Where is this shit? And it was size of long. And then it was size of long. Int signed long. Signed long. Int and unsigned long. And this one was going to be, it was long int signed long signed long int and unsigned long int. All right. Is this unsigned long int? Is that what it was supposed to be? All right, let's see if we can build this. Run task G++. So long variables. So all of these are 8 bytes. I'm curious with this because it says 4 or 8 on his little descriptor in the video. I'm curious why. Right here is what I copied. 4 or 8 bytes. Is this not just more flexible than longs? Like short, I guess, kind of makes sense. But I don't know. I feel like you could have used maybe different numbers. Can I do a third 8 in here and run task? Clear this and then run it again. Yeah, but it's still only 4 for that one. Huh. Recheck if printed the right size of. I mean, it's size of maybe long variable. Terminal, run task. Clear. Yeah, I mean the 888 is assigned 4 bytes in the first one, and then in the long it's assigned 8 bytes. So it seems like it's based on the. Hey yo, how you doing, lazy? I am trying to understand. Then all of these are also just And it seems like in his as well, the long variable was those were also all assigned 4 bytes. And that's the same thing that's happened for me, so I don't think there's anything with the code. I'm just curious to understand what the deal is with 4 or 8.
We are going to go down and really put this in. So we're going to give ourselves some breathing room and paste the code in. So I am going to bring this to the next line. And what we are really doing is printing the sizes for the variables that we have in this group here. Let's build and see if this passes the build. The build is going to be good. Now we can run Rooster. And we're going to see that long is 8 bytes. 8 bytes gives us a really huge range of values. Okay, this is really all we set out to do in this lecture, to learn about these integer modifiers. They modify the way your integer variables behave. For example, we can specify that we only want positive numbers, or that we want to both store positive and negative numbers. For that, you're going to use the signed or unsigned modifiers. You can also shorten or lengthen the range of values you can store in your variable by using the modifiers short and long. And from the output of a program here, you can really see all these effects here. This is really all we set out to do in this lecture. I hope you found it interesting. We are going to stop here in this lecture. In the next one, we're going to start and learn about fractional numbers. Go ahead and finish up here and meet me there.
Unsigned has no negatives. Yes, thank you, Lazy. We also pay attention to the lesson. My question is not about the signed or unsigned values, though. My question is about the amount of data that the long variables and the my question is about long variables, really. I understand how like long longs and shorts show just assign smaller amounts of data or larger amounts of data. Long variable, it looks like it's what it says is 4 or 8, which tells me that it could be which tells me it's dynamic. Like it goes based on what the number that I've input is. But I don't know if that's the case. I guess I could just keep putting numbers in. I just got here. Yes, Lazy, I'm aware. I'm making fun of you for telling me things that I know. What if I just do 5 there? What if I run it now? Run task. If I do 5 8s, does that clear? Yeah, this is still only 4 bytes. How many 8s do I have to enter before it assigns 8 bytes? Try changing it to a number above the 4 byte limit. Looks like it still says. How many fucking... Uh-oh. So now it says long when I mouse over it, so... Run task. Oh. Narrowing conversion from long int to long int. So it doesn't even... Okay. If I get rid of one of those. What about now? Still too much. Okay, that one worked. Oh, whoops, don't want to do that. Clear. It's still only 4 bytes. 2 billion or something. Yeah, so one more above this and it didn't let me do it. The number is, so it's not dynamic. What the hell is this then? What is the point of long? Long, I understand. short, at least I think I understand these. Long seems like it's just integers to me. Like if I make this long, and we'll just call this one, it's still long, longer long variable. And then if I add the 8 back, terminal, run task, G++, clear. Okay. So when I turned it into a long, then it got 8 bytes, and I was able to add the next number. But long just didn't seem to do anything. I think long doesn't do 8 bytes because it would make long not make sense. I mean, it seems to me like it's just it's basically another way of saying integer at this point. I don't know if that's actually true. There was a point in old architecture. So it's really, on most modern computers with a 64-bit CPU, the size of int is usually 4 bytes. I mean, that makes sense. What's the size of normal int? It's 4 bytes based on what we did before. So normal int being 4, and then long being 8, and then short being 2. I mean, unless there's a 6 in there, it doesn't really, I don't see the point of long. And I wasn't able to get any more. All these numbers are so fucking big. Now there's this whole thing. Yes, of course. I think before int was 2 bytes, short was 1, and long was 4, aka 32-bit. And then when 64 architecture came along, it changed. Interesting. So then long doesn't really do anything anymore? If that's correct, then long is just kind of the normal integer thing, and we have to use long. I think it is 4 bytes. It does. And long remained 4 byte for backwards compatibility. I mean, I could see that happening. I could see making something like maintaining that long is 4 bytes so that you can do stuff for older systems that are still using long. I mean, obviously I don't fucking know any of this. I haven't messed with it ever. Long. It's like, yes, I need a 16 byte integer. Let me just put in fucking like mega long. It needs to be long, but like even longer, you know what I mean? Super ridiculously comically long. go on, move to floats and doubles. We did do a little bit with doubles, fucking up our 2.9, and it was like, oh man, it's only an integer, so it's only going to store the 2, and the 0.9 is going to be just completely lost to the ether. It's just not there anymore. It's fake. It's an idea that you created. All right, I'm going to create another fucking. I'm going to create another thing because this one's gotten really long and I don't really want to delete it. Project 5. Woohoo. Alright, let's copy our little shit in. I might need to edit the template a little bit because I don't think the template has a the template doesn't have what is it called? It doesn't have the return 0 on it. But I'll fuck with that another time. Where is it? VS Code. Project 5. Select folder. There we go. Alright, let's watch this video.
In this lecture, we're going to learn about fractional numbers. And as we work with these numbers, I want you to keep in mind that any piece of data you work with in your C++ program is ultimately going to be stored in the form of ones and zeros in memory. Fractional numbers are also called floating
Also, you can run the
types
code from the top right in VS Code.
They are used to represent numbers with fractional parts in
But it's so
C++
much fun to type
and
root.
many other languages. And we have three types that we can use in C++. We have float, double, and long double. And the main difference is in the size they occupy in memory. A float takes 4 bytes, a double takes 8 bytes, and a long double takes 12 bytes typically. So as the size goes up, you can also notice that the precision goes up. So what is the precision? The precision is basically the number of bits you can represent with that type, starting from the number in front of the decimal point. So if we look at this number here, we can try and figure out its precision. So we're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The precision here is 12.
Okay.
If we go back to our table, we really
so
not
doubles
able
can be precise to
represent a
0.15.
number like this with a float. The smallest thing we can use to represent this number well is a double because the precision is 15 and it is more than what we need for this number, which is 12. One thing you should remember is that the number in front of the decimal point is also counted in when you are trying to figure out the precision for your floating point numbers in C++. So here we have an example of how we can declare and initialize floating point numbers in our C++ program. Number 1 is a really huge number, so you can guess that this is more than we can handle with the float. We're going to see how this is handled by our compiler. A double has a precision of 15, so we should expect to store more numbers than we did in a float. A long double should be able to handle
still too
this
big.
without a problem. Because
the long double,
if
maybe.
we go back to our table here, our long double here should be able to handle this better than double, but it is possible that it is the same thing as double, depending on the compiler implementation. And if we try to print out the sizes here, we're going to see what the compiler gives us. We're going to do this when we try this in Visual Studio Code. Okay, and here we are trying to print out the precision of these numbers. We can use a special setting on our stream to control the maximum precision that we can see. Here you see that we are trying to show the precision for each number.
Shut up, lazy.
There is a special setting we can put on stdc out to make it control the precision to a given number. Here we are using 20, and we're going to see that for number 1, this is going to be 7 digits. For number 2, it should be 15 digits or something close to that. The specifics are really dependent on the compiler implementation, and for long double, it should at least be the same as double or even more in some cases. Okay, here we want to see that we can also have narrowing errors if we try to store something big in a float, and a float can't really handle it. Here we have a number with a lot of digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, And we know that a float can only handle 7 digits. So this is probably going to give us a compiler error, as we've seen for braced initialization. If we use functional initialization, this problem is not going to be code at compile time. So we're going to end up with a chunked piece of data, and we're going to see this when we play with this with Visual Studio Code. And another format we can use with floating points is that we can use scientific notation. And it is basically a way we can
We're gonna use scientific
a power
notation?
of
Oh
10
no.
multiplier to multiply with our floating point number. So for example here, number 5 is going to be this number, 192400023. We can use a floating point scientific notation to represent this. So what we're going to do, we're going to say 1.9, and we're going to multiply this with 10 to the power of 8. This is what this means. This E8 here means to multiply with 10 to the power of 8. And if we multiply with that, that basically means moving the decimal point 8 digits to the right. So we can go 1, 2, 3, 4, 5, 6, 7, 8, and it is going to end at these 3
So
here.
it should be exactly the same as the previous number then.
Same number. Number 7 is also another one, and if we do this, we're going to pad with zeros after these 4, and we're going to end up at this same location.
So it won't give the 2, 3, but it will give everything else
We're going to
zeros.
see about that in a minute. And number 8 is another floating point number, and we can use scientific notation to represent it, just like you see with number 9. We're basically going to have the same thing. When we have a minus in here, it means we're going to multiply with 10 to the power of minus 11. And this is going to give us a number below 1. Think 0.007 or something like that.
Well,
so we're going to go 11 digits after the 0 here. And if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and the decimal point is going to go after 3, and we're going to basically end up with the same thing here. We're going to play with this in a minute, and you're going to see that all this makes sense. And don't forget that any piece of data we store
numbers.
in a computer is going
She
to
float
be
on my lung till I double. God damn it,
by
lazy.
ones and zeros in memory. And for floating points, we don't use the number systems like we've done for integers. There is a special system that is used to do that, but it is a little bit complicated to cover in a course like this. I am just going to point you to it if you are interested. And when you are done with this course, you can come up and read on this. The main point is that any piece of data that you represent in your C++ program is going to be represented in terms of ones and zeros in the memory of your computer. Okay, there are a few things you can do with floating points that you can't really do with integers. For example, you can divide with 0. If you take a floating point number and divide that with 0, you're going to get what we call infinity. If the number is positive, you're going to get positive infinity. If the number is negative, you're going to get negative infinity.
No, I don't like that at all.
And you can take two floating point numbers
I don't understand how that works.
Zeros and divide them. And what you're going to get really is not a number. It's something called NaN, which stands for not a number. And your program is going to not crash, but there are a few things you can't do with these things. For example, you can't add them up. You shouldn't really do this. It's probably going to end up bad for your program. Here we have a few examples.
Generally speaking, you try to avoid dividing by 0, from what I understand. All right, so all of these are doubles. Okay.
They are doubles. They must be occupying 8 bytes in memory. Number 10 is initialized to 5.6. 11 is initialized to 0 because we are using braced initialization.
Wait until you learn about triples.
Here. And infinity here is the result of dividing a number by 0. So it's going to be positive infinity because number 10 is a positive number. If you go down, we're going to print number 10 divided by number 11, and we're going to say yields. We're going to put the result out. We're going
They
to
don't
see that
exist. Oh, thank
down
God.
here on the second line, you see that we are trying to add something to infinity, and this is also going to yield infinity, because think of infinity as something super big. And if
Yeah,
you
no
add
shit.
something small to something big, it's still going to be something big. Down here, you see that result equals number 11 divided by number 12, and these
0
two
divided by
are
0.
zeros, so we're going to end up with none, and that's what we're going to print in this statement here down to the bottom. Okay, you should really remember to put in the suffixes when you are initializing your floating point numbers. Otherwise, the default is going to be double. This is what we mean by this. You see this floating number, we have a suffix that is f to mean that it is a floating number. If you don't put that in, this is going to be interpreted as double, and the compiler is going to try and turn that into a float by chopping off things that can't really fit in a float. So to really make it clear that you are storing in a floating number, please put this f suffix here. For double, you don't need to put anything because it is the default assumed by the compiler. But for a long double, you have to suffix this with L, just like this.
I assume it has to be a capital
what
L.
we really mean here. We have seen that the precision for float isn't really enough for many of the computations we might want to do in our C++ applications. Okay, we have talked a lot about floating point numbers. Let's head to Visual Studio Code and actually play with it.
All right.
Okay, here we are in our folder that is going to contain our project. The project is going to be called fractional numbers.
L variable.
So we're going to copy our files, go up a little bit, and put those in, and we're going to go up again and open this in Visual Studio Code. We're going to close whatever it is we have opened now. We're going to close folder, and we're going to open our project in Visual Studio Code.
Okay.
And we're going to do the usual and remove things we don't need in here. The first thing we want to do is to store a few floats in our program. We're going to declare and initialize a few floating point numbers. We have number 1.
Yes. It's not fair. You get to just copy and paste the stuff in because you're the teacher. God. 1.123456789 123456789 F. And then this one is double number 2. 1.123456789 123456789 and then we go to the next one, long double number 3, and this is 1.123456789 123456789 long. I think that's correct. I mean, it's basically just counting to 10 twice. Declare and initialize variables. Print out the sizes. See out. Wrong one. Size of float. And then it's size of float. C and L. Out. Size of double. That's size of double. Probably could have just copied this from one line to the next like I was doing before, but now I'm too far along and I feel weird if I quit doing what I was doing. Size of long double std and L. think this makes
number 2, and number 3. And we want to make it clear that the sizes are what we expect. We are going to open a terminal window here, and we're going to build with GCC, run the task to build with GCC. The build is going to be successful. We're going to come to our terminal, click a little bit, and we're going to type dir. We're going to see that our program is in place. If we run it, we are going to see that size of float is 4, size of double is 8, and size of long double is 16. This is what we expected. Another thing we can do is try and play with the precision.
always with the STD and L, but what about the STD begin W? I fucking hate you, Lacey. God damn it. Begin W? Oh, they always fucking...
Of these numbers and see what we can really go away with. Okay, so we're going to actually put in a piece of code to play with this. We're going to add a setting to our STDC out stream so that we can control the precision. But for this to work, we need to bring in a library that is called io-manip. So we're going to include that
What did
io-manip. And how
io-manip? What the hell is that? Let's include it. Include io-manip. I've never heard of this before.
How do I know this? I usually consult the C++ standard library documentation, and you are not at a point where you can really understand it right now. So we're going to be putting in these things here and explaining them as we go. And I made a typo here. It is io-manip, and you see that now this is recognized. Our program should compile.
All right.
So we're going to
set our precision 20. Controls the precision from std cout. And this is std cout. Number 1 is number 1. No shit. std and l 7 digits. And then with this we go and we'll just change the relevant variables. 2, 3, and this one's 15 digits, and this one is supposed to be 15 plus digits. He calls it 15-ish. What does that mean? I've never heard of io-manip. Makes sense if it's for changing cout settings. I mean, I've never heard of it either, but I'm also not like... this is like my first foray into this, so of course I don't know what the fuck I'm doing. What's going on?
So that we can try this out. We're going to build with GCC. The build is going to go through. We can run our program. We're going to do dir and clear and rooster to run. You see that things start to go off at 6. And if we count what we have here, it is 1, 2, 3, 4, 5, 6, 7. We can only represent 7 numbers accurately with a float.
So I can only represent 7 numbers accurately with a float. So then the first one, it's like what? It's 1, 2, 3, 4, 5, 6, 7. So it goes all the way up to here, and then everything after that is just random by the looks of it. Hold on, if I run this again. No, it's not random. It's just wrong in the exact same way. Okay, that's interesting. Number 2, this was the double, right? So this was supposed to be up to 15. It counts up to here, I think. 1, 2, 3, 4, 5. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So these, after that, it should be wrong. It actually miraculously gets one of the numbers right. And then this one should just be correct. And it looks like it is.
And after that, we're just going to have garbage because the computer can't really make sense of whatever we have after.
It is kind of random, but it will surely be different on different machines.
That we can legally represent
that makes
with
sense.
the float. So the precision for our floating point number here is 7. I really hope this makes sense. Let's check out number 2. We are using double, so precision should be around something like 15. So we are putting in a number 1 through 9, and we are starting over 0, 1, 2, 3, 4, 5 up to 0 again. If we look at what we have in the output here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. 1, 2, 3, 4, 5, 6, and here things start falling off after our 6 here. And if we count, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 digits. This is the precision we are having this compiler for doubles, 17. So it is something around.
Wait a second, actually, now that I'm looking at this. Oh, 1, 2. So for the first one, 1, 2, 3, 4, 5, 6. And then after that, it's the same numbers, it looks like. 8357, 8357, 4676, 4676. So our number 1 is wrong in the same way as on his as him. That's weird, isn't it? And then number 2 is also wrong in the same way. And then number 3, number 3 is just correct by the looks of it. Honestly, never understood how floats and doubles work. What the fuck? Is this not your job? Hello, Tara. Oragna Joe.
15, and we should expect to have something more than that, or at least the same thing as double with long double. So if we look at this, you see that it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5.
So the only thing that we don't have in the long double is the 0.
We are able to represent up to 20, and you can see that long double lives up to even the precision of 20 that we have set with STD set precision here. Okay, I really hope now that you have an idea about these precisions we have with our floating point types in C++ programs. Another thing I want you to see is what kind of narrowing errors we can get if we try to initialize with something that can't really be represented by a floating point number. And here we have a float, it is called number 4, and we are trying to put in something that is bigger than we can really fit in. It has more than 7 digits. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It is more than 7 digits, and we would expect to have a problem with this because we are using braced initialization. Let's try and build this with GCC. We're going to do that. And this is going to build successfully, so this is going to silently chop off our number. If we try to print it out, we're going to say stdcout number 4, and we're going to build again, run the test to build so that our changes are taken into effect. We're going to do dir and do rooster, and this is going to print our number. You're going to see that after the zeros, we have junk. Our number has been basically chopped off. And this is junk because we can't really represent this with the double. The 16 here has been chopped off because we can't basically represent this with the floating point number. If we change this to double, this is going to probably give us what we expect. So let's run again. Build with GCC. The build is going to be good. If we run the program, it is going to show us the same thing. Okay, this is a really good learning change. Why are we having the same results as before, even if we changed the type to double? Try to think about it. The reason is the suffix here is still saying F, and this is going to be stored as float in memory. So if we want this to really be treated like a double, we can take out the float here, And if we build again and run the application, now you're going to see that we see the 23. This is basically being correctly stored as a double. This is a really good thing you should keep in mind. If you don't put in your suffixes here, the number is going to be interpreted as double. By now, I hope you see that if you really try to put more than your floating point can handle, the number is going to be chopped off and only the precision that it can handle is going to be stored in. I hope this makes sense. And
I had a fault where dividing some complex series of additions and multiplications and subtractions gave me 0.99998 instead of 1, and it broke my code.
Well, if you ask mathematicians, 0.9 repeating is actually exactly equal to 1.
But that doesn't help if your code if it breaks your code.
you see that the behavior for numbers is really different. We got a compiler error when we try to do narrowing conversion with integers, but now it is silently chopping off our number. If we try and use functional notation, I think we're going to get the same results. And change this back to a float and use float here. And if we build again,
So let's make this what he made. And so this should be, well, this should break, right? Or not?
Let's go to terminal, run the task, use GCC. We're going to run this. Let's run rooster. And you see that we get the same results. Our 23 is chopped off here. We can also use the assignment notation here, just like we did with integers. And this is going to do exactly the same thing. It is going to chop off the 23 here, and we're going to have some garbage, which is 16 in this case. If we build again, the build is going to go through, and if we run, we're going to see a 16 here. Okay, narrowing conversions are something you should be aware of when storing your floating point numbers, and you should really remember to put in your suffixes here.
It should have been 1, but dividing binary always has a small error, causing a small error because representing real decimal numbers is hard. Sounds to me like a confusing fucking problem, and probably one that you spent many minutes at least, I don't know, trying to solve.
Another thing we have seen that we should really play with is scientific notation. As the comment here says, what we have seen so far.
Oh god, he suddenly added a bunch of a bunch of text. What the fuck? All right, let's clear this. Let's get this shit. Let's get this shit in here. So, science. There we go. Scientific notation. We have seen so far in terms of floating point types is fixed notation. No, you know what? I'm gonna make my life easy. I'm just gonna we're just gonna make this whole thing just a block. Scientific notation is helpful for really large or small numbers. There. I'm not gonna write out his entire little spiel on it. I'm not super concerned because I know what scientific notation is. Double number 5. So let's get this shit in here. 192412323. Double number 6, and this is 1.924123323 E8. Double number 7. 1.924 E8. So he writes here, this can omit the lower, so this part where he writes in can omit lower 00023, that's on here. This just will. It's not that it can. Because this doesn't, this function, or I say function, but it's like this, essentially this math problem doesn't have this at all. It has no reason to add it. For simplicity, if our application allows, like, if we don't need it, yeah, I guess that was fine. Instead of if x is greater than or equal to 1, I put if x minus 0.0, x minus 0.1 times, oh god, fuck me, dude. Easiest fix of my life. I'm sure that worked. I'm not 100%. I don't know how, I don't know what exactly the problem you were solving was. I know that it was the fucking, the fucking, please be 0.0. How many fucking zeros is that? 2, 3, 4, 5, 6, 7, 8. 3, 4, 9, 8. I don't know why you needed to divide something like that. But if it worked, it worked. Okay, let's see.
In floating point numbers is fixed notation. It is what we have here, but we can also use scientific notation, which is exactly what we described in the slides.
Oh, great. Now I have to print all these numbers out. Oh, there's also a number 9 that I almost missed. Double number 9. Fucking 3.498 e to the negative 11. STD, C out. And we're going to copy the fuck out of this. Number 5 is, and then number 5, STD and L. 3, 4. This might be one too many, but I don't remember. 6, 7, 8, 9, 6, 7, 8, 9. That should be correct. Now I have to sleep. All right, man, get some rest. I'm not 100% sure how much more we have. Yeah, I mean, this one this chapter goes on for another 30 minutes of this, and I keep pausing. Like, it's the chapter itself is like fucking an hour and a half long, an hour 45, and we've been we've been at it for almost 3 hours.
And what we have here, for example, is E8, and it means that we are going to multiply
Times
this
10 to
number
the 8th.
here with 10 to the power of 8. If you go down here, we have number 9, so we have 3.498, and we have
That's 10 to
E
the
minus
negative
11. And what this is going to do is multiply with 10 to the power of minus 11. This is how I can represent this here. And we can print these numbers out to really play with them. To make a difference with what we have been doing before, we're going to do stdc out and put a dividing line here. This is one way we can do this. So we're going to do std and dl. We're going to build this. So we're going to run the task to build with gcc 10. The build is going to go through. If we do rooster, we're going to see that our number here, number 5, is what we expect. Number 6.
Hold on a second. Moving a little. Right, run task. Build it. See.
Our number.
Is it because I don't have a space? STD. Oh, it's STDC out. Duh. I forgot the C out part. Of course. Of course. No, it should be fine. Yeah. Okay. So, number 5. All right.
Here, Number 5 is what we expect. Number 6 is the same thing, but we used scientific notation to do this.
Yep.
Because we took this number and multiplied by 10 to the power of 8. Number 7 should be almost the same thing, but
Almost the same.
lower
Doesn't have the 23
here is going to be chopped off because we haven't specified it. We're just multiplying with 10 to the power of 8. So that's why we have 0, 0 here. I hope that makes sense. And if you look at number 8, you see that we stored it like this without using scientific notation. We use
Yeah. So the reason ours is different here is because I made a guess. I didn't actually count how many zeros there were. But the value that it's printed is correct to what I've written. But it is interesting that it prints it in scientific notation for me.
used fixed notation, but on the terminal it's going to be printed out in scientific notation, and this may be pretty cool. The main usage for scientific notation is to make sense of numbers that are really huge. So the way you interpret this, you're going to move these numbers after the decimal points with 0 in front, and it's basically going to be like this. So if you count the zeros you have here, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 is going to be directly after 3, and you're going to get the number here. This is what we mean. And number 9 was explicitly stored in using scientific notation, and you see that we have the same thing. You can play with these things. And
I do think it's interesting that this value, number 9, gets extended like this. 3.49 and 3.498, and then it has this. It looks like it rounds it up, and it does it in the video as well, where it's 9, 7, and then 9 repeating a bunch times 10 to with 3, 7, 2 at the end. I'm curious why this is. Like e to the 10 to the negative 11. I understand that. I'm curious why it does it this way.
Really make sense of them. And again, we didn't specify any suffix here, so these are going to be interpreted as doubles, but this is not a problem because they are doubles here. Okay, we are making some progress with this lecture, which is a little lengthy. The last thing we want to do is to play with infinity and nan. We're going to put a message here to say what we want to do. And we're going to have number 10, which is going to be positive. We're going to have number 11, which is going to be 0. Number 12 is also going to be 0. If we take 10 and divide that with 11, we're going to get infinity because we are dividing a floating number with 0. If we try to print that out, we're going to get infinity, and we're going to get infinity for this result here because we are trying to add something small to infinity, which is something really big. And if we are trying to divide 0 with 0 in floating point, we're going to get what is called not a number. And if we print that out, we're going to see this in a minute. Let's build this with GCC. We're going to...
All right, hold on. I
infinity.
was a little bit slow on putting all that together. Double result. I need to...
0.
Number 10 divided by number 11. And then STD, C out. Number 10. Down. Number 11. Yields. Result. STD. And L. And actually, and this is going to be result plus number 10 yields, and then this should be just plus number 10.
If we try to print that out, we're going to get
All right. Terminal, run task, G++, get our shit all working. Well, that doesn't look normal.
Get infinity, and we're going to get infinity for this result here because we are trying to add something small to infinity, which is something really big. And if we are trying to divide 0 with 0 in floating point, we're going to get what is called not a number. And if we print that out, we're going to see this in a minute. Let's build this with GCC. We're going to build successfully. Let's clear this out so that we don't have noise in here. And we're going to run rooster. And you see here, it says infinity and none, which is what we said here. And if we go down here, it is saying number 10 divided by number 11, and number 11 is 0. You see that here, it's going to yield infinity. If we add 5 to infinity, we're going to get infinity. And if we try to divide a 0 by a 0, we're going to get none, which is really a way to tell you that you're doing something wrong. You should really be careful. One other thing I want you to see is that if you turn this 5 into a -5 and build again, we're going to build with GCC and we're going to run this rooster, we're going to get minus infinity. So if you divide a positive number with 0, you're going to get positive infinity. And if you divide a negative number with infinity, you're going to get negative infinity. And this is what we see here. This is really all we set out to do in this lecture. I hope you found it interesting. And again, the big message is that any data type you're going to be handling in your C++ program is going to ultimately be stored as ones and zeros in memory. And we have learned about floating point numbers, float, double, and long. And they have these properties you see here, and you should use them with this in mind. Otherwise, you're going to have problems with your precision. Make sure you are using the correct precision that you need in your program. We are going to stop here in this lecture. The next one, we're going to try and learn about Booleans. Go ahead and finish up here and meet me there.
All right. So we've done I feel like we've done a lot today. And I think I'm actually gonna go ahead and I think I'm gonna go ahead and call it here. We're like most of the way through chapter 3. I say most. We're like halfway through. We have like the back half of it with booleans, and then there's characters and text. I don't know exactly how much there is that we haven't. Like it's like half an hour of the video. I don't know how much of it is how much more of it I really feel like doing today. So I figure I'll call it here, 3.5 hours, a little bit, and we'll come back to it another day. I do real quick. Let me close this folder and let me open my template folder real quick, just so that I can unfuck that tiny little thing that I keep having to redo every time. Let's unfuck ourselves just a little bit. We'll do return 0. We'll save that. The rest of this, I mean, we just get rid of it every time. I don't know how, I don't think it's that important, but it is like a minor thing that I keep having to change, and I'd rather not have to change it every single time. But yeah, so I hope you guys had a good time, yeah, I hope you guys had a good time hanging out with me today. I had a good time hanging out with you. I'll be back later tonight with some, I think I have Duke Nukem on the schedule, to play some games, and chill this evening. So I look forward to doing that with you guys. I hope you, fucking, I don't know, man. I'm like tired and shit. This is it's a very interesting course, and I'm happy to be doing it. 3 hours is a long fucking time, it feels like, though. So we'll reconvene. I'll be doing this again tomorrow, same time, same bullshit. So we will call it there. Have a good one, guys. I'll see you later. Bye.